Okay, so we're going to to start with the last video. We ended up here in the homework, and now we're going to see simple machines. And what are these? These are mechanical devices that transform forces in order to reduce the effort needed to execute some task. That's what it says. But what do we mean by transform forces? We mean either we multiply the forces so that the one we do in the end is much higher than the one that we are already doing, or we change the direction of the force. And by mechanical, we mean they don't have engines, so it's just with simple elements. When we combine these simple machines, we have compound machines, but we are not going to see that. We are going to see only simple machines and three types: lever, inclined plane, and pulley. So first we're going to see the lever. And you know, Archimedes of Syracuse, he was a genius. He was the one with the density. And Alicia, I remember she knew this story with the density of the king, and he proved that it was not made of pure gold. And well, he was a real genius, and he was the one that said that if he had a lever long enough, he could move the world. By the way, all Greeks, they already knew that the Earth was a sphere, so everything you have heard before is false, because they already knew, like a long time ago. Now people are like wondering if this is flat or not. Greek knew it was a sphere already, and they calculated the radius very accurately. So that's why here is not a mistake that Archimedes is trying to hypothetically move the whole planet with a lever. This is the lever, la palanca, okay? But what is a lever like? Well, it's a bar, or we have important things here is that we have a fulcrum, that is the point of attachment, el punto de apoyo. Okay, that's and then we are doing a force, and that is the force we apply, and we're going to call it effort, and we are going to represent it by an F. And because we need to overcome a force that we are going to call the resistance, R from resistance. And the distance from the resistance to the fulcrum is any distance to the force to the fulcrum is called arm. So we have the resistance arm, that is this distance, and the effort arm, that is this distance from the force of the that we are applying, so the effort, to the fulcrum. That's the the effort arm. And from the resistance force to the fulcrum, that's the resistance arm. And what we know is that the resistance times its distance is the same, is equals to the force that we apply, so the effort times the other distance, the effort arm. This is the law of the lever. So F times dF equals to R times dr. That's the law of the lever, and that's the one that we are going to apply in a lot of exercises. But we have several types of levers, so we're going to see first the class 1, where the fulcrum is located between the effort and the resistance. So the fulcrum is between the effort force, and the resistance in the middle. And that is the first one, so we know is the one that we use when we want to raise something. And here you can see the resistance is the weight, because weight is a force, remember that, not the mass, the weight. And here we are applying the force, and the point of attachment is in the ground, so it's between this force and this force. So that's why this is the basic one, and this is class 1. It is the same as scissors, because here we have the force, we are applying it here, and we need to overcome this resistance, the one of the paper, and here is the attachment point, the fixed point that doesn't move, this thing in the middle. So this is also a class 1 lever. Then we have class 2 levers, and here we have that the resistance is located between the effort and the fulcrum. So the resistance is in the middle, and then we have, so in between the fulcrum and force. For example, here we have, here is the point where the attachment point, the fulcrum, and this is the force we do, so this is the effort, and the resistance is here, because here is where we put all the things we want to move, so this is the weight. So you can see that the resistance is in between the point that is fixed, and so the attachment point, and the effort. And also here, this is where we set our stuff. So this is the fixed point, this is the attachment point, this is the fulcrum, and then the force we do is here with the hand, and the resistance is in the cork here. So it's in the middle again of the fulcrum and the effort. So this is class 2, the resistance is in the middle. So class 1, the fulcrum is in the middle, class 2, the resistance is in the middle, and class 3, the effort is in the middle. Okay, the effort is in the middle. For example, here, here, as you can see, well, just the basic plot, the basic picture here, the fulcrum is on one side, and in the other side we have the resistance, and in the middle we are applying the force. For example, here, I'm applying the force in the middle, but the fulcrum is here because this is the fixed part, and this is the thing that I want to do. So this is the resistance I want to overcome. So I am applying the force in the middle of the resistance and the fulcrum. And also the fishing rod is this kind of lever, because this I put it on the ground normally, and I'm working with this is the effort, and the resistance is in the top of at the end. So again, the effort is in the middle, and in the middle of the fulcrum and the resistance. This is in Spanish, you know, I'm mixing things. So these are levers. Then we have inclined plane. That's another simple machine, and it's just a flat surface that is inclined, so it has an angle with the horizontal, with the ground. And as you have used, I guess, it's easier to lift bodies here than to lift them like this, like totally without any help, because we apply less force if we move it upwards. But we are going to move it a longer distance, so it's not free. I mean, we apply less force, but we're going to carry it for a greater distance. And when we have here the loader, you will see it, why this is in fourth of ISO. But so right now you have to understand that what is equals here is that this distance times F, so the effort we do, is equals to the height, that's why it's called H, the height times the resistance. Okay, so this is what we have for inclined plane. And finally, we have pulleys. Here we are not going to see any formula for this, but here the force is the same. So the effort is the same as the resistance, but this helps us to move things easily, because if you want to lift a stone, a big stone like this, it's really difficult. But if you can pull downwards, not upwards, it's a bit easier. So what we change here is the direction. We don't change the force with the level 1, at least. We don't change the force. the amount of the force, but we can choose the direction, and that helps. If we put more pulleys, then we're going to apply less force, but it's not the scope of this year, so we're not going to do it. So the pulley, as you can see, and as it's la polea, it's a wheel and that turns around an axle, and we pass a rope, and that's the one you use in wells, for example, to have water. That's how you can do it, and it's much easier than if you try to pull out the water like this. That's why in every well we have a pulley. Okay, so let's see some exercises. We use a 1.5 meter bar to move a 750 newtons rock. If the maximum force we can apply is 300 newton, where must the fulcrum be? So let's see, the data I have is that the total distance is 1.5 meters, that the resistance is 750 newtons, and that the maximum force we can apply is 300 newtons. So where must the fulcrum be? So fulcrum x, I don't know, that's the distance. So that's the data I have. I'm going to draw it to know what I'm talking about. So I'm saying that I have a bar, and the bar is 1.5 meters, and I want to overcome a resistance that is 750 newtons, and I want to apply a force of 300 newtons, that's the effort, and the fulcrum, if if no one tells you otherwise, we're going to assume this is a level 1, so that's why I put it in the middle. Okay, so the formula I'm going to use is the law of the lever, that, as you know, is F times dF equals R times dr. And so the first thing is that I'm going to define my distances. So I know this is 1.5 meters. And this distance, that is dr, because it's the arm of the resistance, and this is the arm of the effort, this distance is the one that I'm going to call x. Okay, so this distance is the where the fulcrum is, because it's the shortest one, so I'm going to choose this one as the distance. Then, because everything, the total bar is 1.5 meters, if I remove this part, if I remove this part, then this part here is exactly dF, because it's from the fulcrum to the effort. So that's the arm of the effort. That is exactly, as I have already said, 1.5 minus this part. Okay, so dF is 1.5, the total part, minus the dr. And because I have called dr x, I put 1.5 minus x. Okay, then I apply the formula. And so I say that F times dF equals R times dr. And I'm going to put the data I have. So F is 300, okay. And then dF is this quantity, with parentheses, because it's a subtraction and I need to multiply, so parentheses, equals to R. R is 750 times dr. Okay, dr is x. So here is just the values here, and this is an equation, first grade equation, and I'm sure you know how to do this. First we do the multiplication, so 300 times 1.5 and 300 times x, this is here, and this 750 times x is 750x. And then if I say, okay, this 300 times 1.5 is 450, and this x, I'm going to move it to the other side, so instead of a minus, it's going to be a plus on the other side. And then I add up this two, that's 1050x, and finally I'm I'm going to move this one that is multiplying the x, I'm going to move it to the other side, dividing. So 450 over 1050, and that's 0.43 meters. That's the x, and that's this, and that's the distance that they asked me. So this is what you have with all the colors in the PDF. And another exercise that's about the inclined plane. We wish to get a box of 1500 newtons up to a height of 1 meter. How long should the ramp be to lift the box without applying more than 200 newtons? Okay, let's see what it means. So first we have an inclined plane because I want to lift this 1 meter, okay? And I want to have a ramp that's an inclined plane. That's how I know. So this is the same picture that I had before. And let's see the data here. So the box, so this box, the resistance is 1500 newtons. Okay, the height is 1 meter. So this h is 1 meter. How long should the ramp be? So they are asking me this, the distance of the ramp. To lift the box without applying more than 200 newtons. So the force I want to apply, the effort, is 200 newtons. So I have everything. And I'm going to use the formula of the inclined plane. That's F times D equals R times H. So I have everything. I'm going to put it inside. F is 200 newtons. X is so D is X, equals R is 1500 newtons, and H is 1 meter. So I have everything here, and I want to have the X, so I'm going to move the 200 to the other side, and because it's multiplying, I'm going to move it to the other side, dividing. So I'm going to have 1500 times 1 divided by 200, and that's 7.5 meters. So that's the distance the ramp should be if I want to apply this force. And this is everything, and with this we have finished the units. So these are the final exercises, and yep, so next video will be from the next unit. See you then.